Right, in this chapter we're going to learn about the Laplace transform, and really the Laplace transform gives us another way to solve differential equations. And what's particularly useful about it is that it turns a problem like a differential equations problem really into an algebra problem. The Laplace transform is one of several integral transforms that exist. An integral transform is a relations where you kind of plug in one function. Right, so what we plug in is some function f of t, and what it spits out is this other function, big F of s. Right, so it's a way we generate some function by plugging in another function. Now, the things that change depending on what the integral transform is the kernel. So what defines a particular integral transform is what we call the kernel. It's this function, big K of s and t, so it's a function of both s and t, and then what these limits are. So once we fix the kernel and those limits, then we know what transform we're talking about. It's possible that one or both of those limits of integration could be infinite. With the Laplace transform, which is what we're going to focus on in this class, the kernel is the function e to the negative st, and the limits are from 0 to infinity. In order for the Laplace transform of a function to be defined, we just need the function to be piecewise continuous, which means that if you graph it, at least each individual piece of the function is continuous. There might be some jumps in the function, but it doesn't have to be strictly continuous. So we find the Laplace transform, and we denote that Laplace transform. We use a little scripty L here, saying we're taking the Laplace transform of the function f of t, and it spits out another function, big F of s. And we integrate from 0 to infinity, e to the negative st times f of t with respect to t. So we generate the function f of s from the function f of t. If I'm going backwards, if I know the function big F of s and I want to know what function I had to find the transform of in order to get that function, we are said to be finding the inverse transform. So little f of t is the inverse Laplace transform of big F. We're going to use this integral definition to derive the Laplace transforms of some simple functions. And so we're going to start with a simple function, the function f of t equals 1. So we're going to find big F of s, or the Laplace transform of 1. And this function, big F of s, is defined to be the integral from 0 to infinity, e to the negative st times 1 dt. A little review from Calc 2. This is an improper integral because it has an infinite limit of integration. So we're going to set it up as a limit as b approaches infinity of the integral from 0 to b e to the minus st dt. Now we know how to do this integral. S is another variable, but keep in mind we are respecting t. So when we see this integral, that means any variable that isn't a t we treat like a constant. So that s is like a constant. So when we integrate this, now we're going to carry the limit as b approaches infinity. When we integrate this, we get negative 1 over s e to the negative st from 0 to b. We'll plug in these limits of integration. So negative 1 over s e to the negative s times b, and then subtracting another negative, so plus 1 over s e to the, when we plug in t equals 0, that's just e to the 0. Now we're letting b approach infinity. As b approaches infinity, this exponent approaches a huge negative number, right? The exponent approaches like negative infinity. That means e is being raised to a huge power in the denominator, right? I could rewrite this just to kind of make it a little bit more clear. Negative 1 over s times e to the sb, positive sb in the denominator. And of course e to the 0 is equal to 1, so I'm going to drop that here. Now as b gets huge, this fraction has to go to 0. Right? That denominator blows up, so that part goes to 0, and we just get 1 over s. So 1 over s is the function f of s, or the Laplace transform of the function 1. All right, let's find another transform. This time we're going to start with the function e to the at, and we're going to find its Laplace transform. So this function, big F of s, is the Laplace transform of e to the at. And again, this is where we assume that a is some constant. So using that definition, it is the integral from 0 to infinity, e to the minus st times e to the at dt. T is the only variable. A is some constant. S we're treating like it's a constant. I'm going to do a little work simplifying using rules of exponents here. And at the same time, I'm going to write this as the limit that I know it is, right? We're integrating from 0 to infinity, so we're going to take the limit as b approaches infinity of the integral from 0 to b. Using rules of exponents, we can write this as e to the negative s plus a times t with respect to t. This is just like integrating the last one, right? I have e raised to a constant times t, basically. So it's the limit as b approaches infinity of 1 over negative s plus a e to the negative s plus a times t, evaluated from 0 to b. I'm going to plug in the limits, and at the same time, I'm actually going to do a little something to rewrite this expression, just kind of factoring. I'm going to factor out a negative 1 from each of those expressions. So we're taking the limit as b approaches infinity. Then we have negative 1 over s minus a times e to the negative s minus a t. And now I'll plug in those limits. And let's see, we're subtracting a negative, so plus 1 over s minus a e to the 0. Now as b gets huge, again, this exponent becomes a huge negative number. This fraction again goes to 0. E to the 0 is of course 1, so we get 1 over s minus a. And this is true as long as s minus a is greater than 0. That's the conditions that make this approach 0 when b grows to infinity. A great thing about the Laplace transform is that it is a linear operator. That means that we can split it up over addition and subtraction, and we can pull out constant factors. So that's just basically what this says here, what this equation here says. And the nice thing, the reason that this helps us is that sometimes we could find some integrals, or some transforms rather, without having to do the whole integral. If we know some transforms, we could use the linearity of the transform and maybe some other facts, how we can rewrite the function in order to find the transform without having to do the actual integration. So here's a really cool example of that. We're going to find the transforms for cosine omega t and sine omega t. Right, so we're going to do 2 of them. And what we're going to do is we're going to use the fact that Laplace is linear, and we're going to use Euler's formula. Right, that e to the j theta is equal to cosine theta plus j sine theta. You saw this in pre-calc or tech math, whichever one you took, if you took it at Vermont Tech, and maybe you've also seen it in some other courses, but this is one of Euler's most famous equations. So what we're going to do is we're going to consider the function f of t equals e to the omega t j. and we're going to find the Laplace transform of this function. Now, if e to the omega tj is equal to cosine omega t plus j sine omega t, then that means we're going to find the Laplace of cosine omega t plus j sine omega t. Now the Laplace transform is linear. I can split it up over addition, and also when I'm at it, I can pull out these this constant multiple. J is a constant, it's just complex. So we've got the Laplace transform of cosine omega t plus j times the Laplace transform of sine omega t. So here's what our strategy is going to be. Like our takeaway from this line right here is that we're going to find the Laplace transform of e to the omega tj. That will be an expression that's going to have a real part and an imaginary part. It will be complex, and that's okay. Once we find that, though, the real part is going to be equal to the Laplace transform of cosine omega t, and the imaginary part will be equal to the Laplace transform of sine omega t. So all we need to do is find the Laplace transform of e to the omega tj. And I'm going to just rewrite this slightly. I'm going to call this a Laplace transform of e to the omega j times t, because I want to think of it as just a single constant coefficient on t, so that omega j. Well, we know what the transform of e to the at is, where we have some constant in front of t. I'm just going to use that same transform that we found. On the last page we saw that it was 1 over s minus the constant, so s minus omega j. So that's a complex expression. I can tell because there's a j involved. It's in the bottom. What I want to be able to do is write it in the rectangular form, like the real part plus the imaginary part, not in the denominator. And so in order to do that, we'll multiply the top and the bottom by the complex conjugate. Over s minus omega j. So I'm going to multiply top and bottom by the complex conjugate. That's what we get when we just switch this subtraction to addition. So on top we get s plus omega j. On the bottom, we're going to FOIL that out. We can do a little bit of that on the side here. S minus omega j, S plus omega j, S squared minus S omega j plus S omega j. And now here we have a negative omega squared times j squared, and j squared is of course -1, so that's a plus omega squared. So splitting it up over the addition in the top, we get s over s squared plus omega squared plus j times omega over s squared plus omega squared. And look, here we have it. This is the real part here. This is the imaginary part. And so we've got our transforms for cosine omega t and sine omega t. Transform for cosine omega t is s over s squared plus omega squared, and the transform for sine omega t is omega over s squared plus omega squared. All right, next we're going to find the transforms for the hyperbolic sine and hyperbolic cosine functions. You may have run into these in previous calculus courses. If not, they're just defined as follows in terms of these exponential functions. So we can use the linearity of the Laplace transform to get these. We don't have to do the whole integral. We'll start with hyperbolic sine. So hyperbolic sine of AT, where a is some constant, is, I'm going to distribute this factor of a half. So we get 1/2 e to the t minus 1/2 e to the negative t. And that means that the Laplace transform of hyperbolic sine of AT, I'm going to split it up over the subtraction. I'm going to pull out the constant factors. So we get 1/2 times the Laplace transform of e to the, this is AT, e to the AT, and then e to the negative AT here. So we get 1/2 times the Laplace of e to the AT minus 1/2 times the Laplace of e to the negative AT. We know the transform of e to the AT. That's what we found a couple pages ago. So this is 1 over s minus a minus 1/2. And then here you can use that same transform, only the constant is negative a. And that gives us 1 over s plus a. I'm going to write this as a single fraction. So I need a common denominator. Do a little algebra here. So our common denominator is 2 times s plus a times s minus a. On top we have s plus a minus parentheses s minus a. Simplifying, let's see, up top we have 2a over 2 times s squared minus a squared. Cancel those 2's, and we get a over s squared minus a squared. So that is the Laplace transform of hyperbolic sine of AT. We'll do the same thing for hyperbolic cosine. Hyperbolic cosine of AT, that means I'm finding the Laplace of 1/2 e to the AT plus 1/2 e to the negative AT. We can use the linearity. So we get 1/2 Laplace of e to the AT plus 1/2 Laplace of e to the negative AT, using those same transforms. And we've got these factors of a half to pull down. So 1/2 over 1 over s minus a plus, now 1/2 times 1 over s plus a. Doing the same thing here, going to get a common denominator. So we can add these fractions. So our denominator is 2 times s plus a, s minus a. Up top we have s plus a plus s minus a. Now on top we have 2s. On the bottom, 2 times s squared minus a squared. cancel those 2's. And we get s over s squared minus a squared. And there is the Laplace of hyperbolic cosine of at. So we didn't have to do any integrals. We were able to kind of put it together using the transform of e to the at and the linearity of the Laplace transform. The table on this next page just has some transforms. Some of them we derived ourselves, and then some extra ones that you could derive using the integral definition or the linearity and some of the other transforms we know. Just one quick note here. We see the n factorial here. That's just defined. N factorial is defined in the following way. I'm gonna give it to you twice. So its definition is recursive. The first part is that 0 factorial is always equal to 1, and that n factorial is n times n minus 1 factorial. So that's what I mean when I say it's recursive. If I know n minus 1 factorial, I can use it to find n factorial. Intuitively, what I think of when I see the factorial is just the product, multiply all the integers from 1 up to n. That's basically works for all positive integers except for 0. By definition, 0 factorial is 1. And you've seen the factorial when you took Calc 2 and did infinite series. That usually comes up. The other new piece here is this, which we probably won't need, but this is called the gamma function. And it's an extension of the factorial over the reals. So this idea of n factorial is obviously only defined for integers, but this is a way, the gamma function is a way that mathematicians try to extend that notion to apply to all real numbers and not just the counting numbers. It probably won't come up in any of the applications that we see, but you will see it in basically every table of a Laplace transform. All right, now we're going to find the Laplace transform for yet another function. But again, I probably don't need to tell you, we're going to be able to do this without having to do the whole integral. The first thing I'm going to do is just, we're squaring t squared minus 3, so we're going to square it out. So our function f of t is equal to t to the 4th minus 6t squared plus 9. There's f of t. So now what I'm going to do is just go straight to f of s. I'm going to use the linearity. Now I could sort of write it out the way I did before, kind of explicitly stating that I'm splitting them up, but I'm just going to kind of pull each piece down. So we're going to have the transform of t to the 4th, and then minus 6 times the transform of t squared plus 9 times the transform of 1. So the transform of t to the 4th, going back to this table, is 4 factorial over s to the 5th. I'm looking here. And then using the same rule for t squared, that'll be 2 factorial over s cubed. And then the transform of 1 is 1 over s. Now I'm just going to clean this up a little bit before we simplify. So 4 factorial, 4 times 3 times 2 times 1, that's 24 over s to the 5th. 2 factorial is just 2 times 6 is 12 over s cubed plus 9 over s. I'm going to get a common denominator, which is s to the 5th, so this needs an s squared, this needs an s to the 4th, s to the 4th. So our common denominator, s to the 5th, up top we have 24 minus 12s squared plus 9s to the 4th. There's the transform. So we're trying to be clever about like just how we write a function. You know, like finding another way to write it will help me work less hard to get the transform. And that is really on display as well in this next example. So we're going to find the Laplace transform for the function sine squared of 4t. Now we found the transform for sine, but you can't just square a transform. The operator, the Laplace transform is linear. That means you can split it up over addition and subtraction and pull out constant factors only. It doesn't mean you could square the whole transform to get the transform of a square of a function, or that you could multiply two functions of t together. So we have to be a little bit clever. It's kind of in the way that we would have to be clever about rewriting something when we're learning how to integrate. We know that integrating a function is all about how you see it and finding a clever way to write it that allows it to reveal its form to you. So we're going to do the same thing here, and we're going to find that use the half-angle identity for sine. And if we use the half-angle identity, we find that sine squared of 4t is equal to 1 minus cosine of 8t all over 2. Notice, here's what I like about this. There's no square right there. That's just plain old cosine. So I'm going to rewrite this. I'm just going to split up this fraction. But we're going to be able to do this using the transform for the cosine function, which we already found, and also the transform for the constant. Oh, this is 1/2 minus 1/2 cosine of 8t. And so the Laplace transform of sine squared 4t is equal to, I'm going to use linearity, I'm going to split that up. So I'm going to have 1/2 times the Laplace transform of 1 minus 1/2 times the Laplace transform of cosine 8t. 1/2 times the Laplace transform of 1 is 1 over s minus 1/2 times the Laplace transform of cosine 8t. Just kind of go back to the table, right? We derived this. Cosine omega t, s over s squared plus omega squared. So for us, omega is 8. So that'll be s over s squared plus 8 squared. Clean this up just slightly. Get a common denominator. The first fraction needs to pick up s squared plus 64. The second one needs to pick up an s. Up top we have s squared plus 64 minus s squared, so those cancel, and we just have 64 divided by 2s s squared plus 64, and now we can cancel a factor of 2, reduce this. And there's the transform of sine squared 4t. This next result tells us how to find, again, transforms of other functions. And in particular, we talk about s shifting here. So what happens when we replace s with s minus a? So suppose I have a function f of t, and I know that its Laplace transform is f of s. Then I can find the transform. The transform for the function e to the at times f of t is just f of s minus a. So see how that factor of e to the at just replaces, it shifts that function down by a units, I guess you could sort of think of it that way. So here it is sort of written in this way. And then of course if we're thinking about going backwards, and this is where we're going to actually see it in these next couple examples, that if I have, if I want the inverse transform of f of s minus a, that's going to be e to the at times f of t. And this is a way to help us recognize the inverse transform from something that looks really close to an inverse transform, but like maybe if we just see, oh, it has this basic form, but it's shifted down so many units. This is how we make that adjustment to find the function of t that we're after. And so you'll see what I'm talking about in this next example. We're going to find the inverse transform for this function. So this is our big F of s. Right, there's our function of s. And I want to find the function of t, the little f of t, that has this function as its transform. We have this quadratic in the bottom. And, when I think of quadratics in the bottom, if I were to go back to this table, thinking of quadratics in the bottom, I've got, I've got these sort of basic forms here, and then I've got some more stuff going on here. But look how they're all written as a form of either a sum of squares or as a difference of squares. And what we have is just a general quadratic here. And if I want to write it in a different way, we're going to do one of my favorite things ever in the world to do, and that is we're going to complete the square on this quadratic. So we've got s squared plus 2s plus 401. And I'm actually going to leave a little space here. And I'm going to complete the square. So I've kind of segregated out that 401. And so now I'm looking at the coefficient on s here, so I'm going to add 1 squared and then subtract 1 squared. And this stuff here, that's a perfect square. So that is s plus 1 squared plus, and then this will give us 400. In other words, we have s plus 1 squared plus 20 squared. All right, now, if you take a look at what we've got, certainly it looks like we've kind of replaced the s squared with an s plus 1. This is like an s shift, right, where a would be -1. Of course, we haven't rewritten the whole function yet, but just when I start to see this form here, this is what I'm thinking, that we're going to have an s shift where a is -1. So let's use this. We're going to rewrite this function. We still have a bit of work to do. So the Laplace of f that they give us is 3s minus 137 over s plus 1 squared plus 20 squared. Now, if that were just an s plus 1 up top or a 20 up top, we could go to that table and find the inverse transform. But we're going to have to be a little bit clever about how we rewrite this. I've got that 3s. So if I had, I'm just thinking ideas here. If I had 3s plus 3, then I could take out a 3, and then I'd see that s plus 1 in there, and I could factor out the 3 out in front. We're going to make that happen. I'm going to add 3, and I'm going to subtract 3. Now I'm going to rewrite this part here as 3 times s plus 1. And then we have minus 140 We're getting closer. What I'm going to do next, now let's take a look up here again. When I look at the, we've got a sum of squares, so I'm kind of looking at these guys right now, and I want to have just the s or just the omega, or I guess we could come down here and look at these forms, right? We could sort of actually see in these formulas that looks like an s shift, like that theorem was talking about. But I want to have one part that's just the s minus a, whoops, where I have the s minus a that matches that part down here, and then I want another piece where I have the omega that matches that omega down there. So I'm going to split up that fraction. I'm going to split it up over the subtraction that's happening up top. So I'm going to split it right here. And for this first piece, I'm going to take the factor of 3 and put it out in front. So I've got 3 times s plus 1 over s plus 1 squared plus 20 squared minus. Now here I've got a 140. I really want that to be a 20 because I want that to match what's down here. So I'm going to factor out a 7. So this is 7 times 20 over s plus 1 squared plus 20 squared. I'm going to pause and take a breath here because I just want to acknowledge that what we're doing here to kind of help us find the inverse transform is not unlike, you know, some of the techniques we would have to employ to integrate functions back in Calc 2. You know, basically, you know, this expression is horribly unsimplified. This is not a simplified expression, but it's the useful one, right? So we're being creative in finding useful ways to unsimplify this fraction that we started with to make it possible to find the inverse transform. So now, if I use that table, this is an S shift, like right here. The inverse transform of this is the cosine function that's shifted down 1. So I've got my factor of 3. This tells us the shift. This plus 1, that tells us that the shift is a equals negative 1. So that's e to the negative 1 times t, or e to the minus t. And then this is the cosine of 20t. And let's see, this was up top, this is the Laplace transform of f, so down here this is actually f of t, right? These two are not equal to each other. Now we're finding the inverse transform. And then we have minus 7 times, and the same thing, same shift. Shift is by negative 1, but this time the form is sine. So 7 times e to the minus t sine 20t. And there is our function. We're going to do one more here where we find the inverse transform. Again, we've got this quadratic on the bottom, but it's not like there's no s term, so we're not going to complete the square on it. Instead, with this one, I'm actually going to find the partial fraction decomposition. So let's use partial fractions. So 2s plus 16 over s squared minus 16 is s plus 4, s minus 4. And when I have distinct linear factors, as we do, the s plus 4 and s minus 4, that means that we're going to set this up as some constant a over s plus 4 plus some constant b over s minus 4. We're going to multiply both sides by the LCD, which is, of course, s plus 4, s minus 4. When we do that on the left, the whole denominator cancels. We get 2s plus 16. On the right, we're going to distribute that factor, and at first we're going to get, for that first term, a times s minus 4, and for the second factor, b times s plus 4. Now there's different ways we could solve for a and b here. That is our goal, to figure out what a and b are. When we have distinct linear factors, I think the easiest way to do this is just find some convenient values of s. If s happens to equal 4, right? If this equation is true, it's got to be true for all values of s. So that means it would be true when s is equal to 4. And if s is equal to 4, then that means that, let's see, 2 times 4 is 24 on the left side is equal to, if s is 4, then this first term here zeroes out. And then we just get b times 8, or 8b. And that tells us that b is equal to 3. On the other hand, if s is equal to negative 4, then we get, let's see, on the left side we get 8. On the right side, the b term would cancel out, and we get negative 8a, and that tells us that a is equal to negative 1. So now that we know what a and b are, then we know that the Laplace transform of f, substituting in these values for a and b, is negative 1 over s plus 4 plus 3 over s minus 4. And I'm going to pull out these constant factors, so negative 1 times 1 over s plus 4 plus 3 times 1 over s minus 4. These are both ones that we know, right? Like these fit. In fact, we derived, we derived that transform. That these are the transforms of e to the negative 4t and e to the positive 4t respectively. So this is L of f, and that means that f of t is negative e to the negative 4t plus 3 times e to the 4t. There's actually another way to do this one as well. If we look at the original form that this function took on, it wasn't, there was no s term, so completing the square wasn't something we were going to do. However, you might have recognized this as being, we have this difference of squares, right? This is s squared minus 4 squared. And if we scroll up to that table, the difference of squares is where we had the hyperbolic sine and hyperbolic cosine. So we could use some algebra to rewrite this in a different way and find the same function in the end. And so that's what we're going to do. I'm going to just start a new page and just show you another way to do this problem. So here they told us that L of f was equal to 2s plus 16 over s squared minus 16. So I'm going to do a couple of things. First of all, I'm going to separate it out. I'm going to split it up over this addition, and I'm also going to write this 16 in the bottom as 4 squared. So we have 2s over s squared minus 4 squared plus 16 over s squared minus 4 squared. We're not quite done. In order to fit that form in the table, I just want a plain old s up here and not the 2, so I'm going to segregate out. I'm going to pull out this factor of 2. 2 times s over s squared minus 4 squared plus. And for the other one, if I have a constant up there, I want that constant to match this constant. I want that to be a 4. So I'm going to pull out a factor of 4. 4 times 4 over s squared minus 4 squared. So this is L of f. And now we can use that table. If you use that table, you'll find that this part here is the transform for hyperbolic cosine of 4t, and this part here with the 4 on top is the hyperbolic sine of 4t. So we get 2 times hyperbolic cosine 4t plus 4 times sine hyperbolic, 4 times hyperbolic sine of 4t, and of course this equals I carried down, not quite there yet. This is f of t, right? So I don't just want to carry down the equal sign. It is a whole new function of a whole different variable. So there's our f of t. It doesn't look the same right now, right? We got this exponential one, but then we just go back and use the definition of those hyperbolic functions. So hyperbolic cosine of 4t is 1/2 and then e to the 4t plus e to the negative 4t times hyperbolic sine is 1/2 e to the 4t minus e to the negative 4t. Going to do some simplifying, so let's see, those cancel, these cancel, get a factor of 2 out there. Going to distribute that, so we have e to the 4t plus e to the negative 4t plus 2 e to the 4t minus 2 e to the negative 4t, and altogether now we have 3 e to the 4t minus e to the negative 4t. And that is precisely what we got doing it the other way. So in this case, there is more than one way to get to the desired result.